Hello and welcome back, and in this video we'll be looking into the numerical examples pertaining to the bubble sort. In the previous video we focuses on the overview or the conceptual background of the bubble sort algorithm, and in this video we'll be looking at some of the examples, numerical examples, to understand this algorithm and also to visualize this particular algorithm. Without a further ado, let's get started. Let's take an example. This is a particular list have 5 entries or an array of 5 entries, and this represents the rank obtained by 5 students in a class, and we want to sort them using bubble sort, and the order which we need to sort is the ascending order or the increasing order. So we want to sort the entries in terms of increasing order. And you can see this is an unsorted list, so we use a bubble sort algorithm to sort this, right? So first we will be taking this and we'll be studying some of the important concepts pertaining to the array. Even though we have separate sections on the array, but let's take quickly about these things, right? So the array, the first entry is 0. These are the index. This is not the number corresponding to the entry, but these are the index to reference this particular value or this particular cell. And 0, 1, 2, 3 and 4. Since n equals to 5 entries, the number ranges from 0 to 4. Why? And the array length, as I told you, n equals to 5. And these are the actual entries: 7, 5, 4, 9, 3, 7, 5, 4, 9, 3. And you can see this is represented by A0, A1, A2, A3 and A4. So these are the index. So A of that index will, a small a of this index will give you this particular entry, right? Something like that, right? And we know that from the previous lecture we learned the number of pass required for the sorting, bubble sorting, is n minus 1, which means we have 5 entries, so 5 minus 1 is 4. So we need 4 passes by 4 steps. You can even call 4 iterations or 4 steps. But you can call iteration because in every passes we have an iteration. We can call steps. 4 steps are required to completely sort this entries in ascending order, right? Something like that, right? And we can even calculate total iteration. Basically it is an arithmetic progression based formula, n into n minus 1 divided by 2, where here the number of entries is 5. 5 into 5 minus 1 divided by 2. 5 into 4 is 20 divided by 2 is 10. So the total iterations is 10, right? So we need 10 iterations to completely sort this unsorted list into a sorted list, right? So let's get started. So this is the first time I'm just giving you this particular table overview, and from this table we'll be using various methodology or the procedure of the bubble sort to sort the unsorted list. And there's a given problem. We have deliberately given a sparse number, iterations, and you can even see comparisons and swapping. So I'll tell you why we have got both this particular thing. So some people find it very difficult to compute only in this particular array, so I have brought in with the swapping mechanism also, so that you can really understand why we do this swapping and something in a separate array or something like that, right? Let's go for the first pass. In the first pass you can see number of comparisons is n minus 1, so which means we have 5 entries. 5 minus 1 is 4, so we will have 4 iterations. That is why in the first pass number 1, we have got 4 iterations. And do not worry about this, the 0, just I wanted to bring in the previous steps value, right? So since this is the first iteration, this is the original problem, and these are the 4 iterations that will be taking a look at it, right? Let's go to the first iteration. First step is earmarking the first 2 entries. It's a pairwise comparison. So in this case, the array 0 and 1 is checked, and you can see array 0, the number is 7, and array 1 is number is 5, and we are doing an increasing order. So which means that I'll just go back to my lecture once again. For an ascending order, if the previous entry is less than the next entry, then no swapping. But if it is vice versa, if the previous entry is greater than the next entry, then we need a swapping, right? So that's the basic logic. In this case, 7 is greater than 5. So the previous entry is greater than this, or you can even say the first entry is greater than the second entry. So in this case, we need to swap. So we need to swap such that this will become 5 and 7, so that the logic maintains. So we are creating an ascending order sorting. So then the final, we can call this I and j. J should be greater than I, right? So we swap it. So that's how we can see 5 gets swapped, 5 gets swapped, and it's given here. And then this particular table will bring it here, like then this 7 and 5 gets sorted, right? So this bubble gets moved to this array number 1. Now we'll have a comparison. This will become I and this will become j. So say is 7 greater than 4? Yes. Array of 1 is greater than 2. What we have to do? We have to swap it or interchange this, right? So 5, this already done. This is 4 and 7. You can see 4 gets swapped in 7th place and 7 gets swapped in 4th place, or this 4 initially it is in array 2 gets moved to array 1, and 7 which is in array 1 gets moved to array 2, and then this table gets replicated here, and you can see 5 4 is done. Now this particular 7, it's already moved here, that is why it is still marked in red. And then you can see 7 and 9, which one is higher? It's 7 or 9. So 9 is higher, so A2 which is less than A3, and then we don't need any swapping, right? So if it is higher than this, then we do a swapping, and if it is lower than this, we don't do any swapping. So in this case A2 is less than, so we'll just write that in the swapping. We don't do any swapping at all. You can see in the swapping, you see blue colored and red color. Red and blue becomes blue and red, but here in this case red and blue is still red and blue, so we don't have any swapping. And then we will bring back to this the final iterations. The final iteration will yield a value, highest value at the right. So I'll tell you what that means. So this gets moved here, like so 9 and 3. We'll do a pairwise comparison of 9 and 3. So 9 is greater than 3, so we'll do a swapping. So this is 3 and this will become 9. So in the first iteration, the maximum number gets moved here, right? So in an ascending order sorting, the maximum number was somehow managed to move here. So that's one basic understanding. So which means that we will be eliminating 9 in the next pass onwards. We'll not consider that for swapping or finding the biggest among the adjacent numbers, right? So that's how I've just marked with a square brackets, which means that it is touched now. So we need to only compute using these things. That is why you see the number of comparison is n minus 1, and now we exclude this. So the number of comparison is passed to is n minus 2. We don't have this, so it becomes n minus 2, right? Something like that. And we can see this is one, this 0 is from the previous final thing, like 54739. 54739. So and swapping is also the same. Now we will check from the beginning. So 5 and 4. Is 5 greater than 4? Yes. So we need to do a swapping, right? So we change 4 and 5, 4 and 5, and then we'll bring back to here, and then we'll move to instead of 0th, we'll move 1 and 2. We'll check, is 5 greater than 7? No, right? So we'll just keep the same position, and then we'll bring back to the third iteration and we'll check 7 and 3. 7 greater than 3, obviously it is greater than 3, so we'll do a swapping. When we do a swapping in the second pass, we see that the penultimate maximum or the second maximum gets sorted here beautifully, right? We can see since we have got only few numbers, the few entries we can visualize here, like the third iteration or third pass we'll only get this 3, 4, 5 and 3, something like that. So this 7 is the maximum among 4, 5 and 3, and it can see is beautifully bring back to the last or penultimate position. And in the third pass we will do a squaring of this, provide a box over this 7. So 7 and 9 are not touched in this particular iteration. We have to go back to the original position. So this 0th is from the previous iteration, previous pass, and the iteration number 1, 4 and 5. You can see every pass the number of iteration or the comparisons, which we can even call this as a comparison, but to in order to make distinct, I just had iterations. This is 3, right? So pass is 3 and n minus 3 passes. So n here is 5, so 5 minus 3 is 2. So we have got 2 comparisons, remember? Like, so the logic is valid. Why? Or you can even make a table of 0 to 4, and for the pass you can even still have 4 and you can strike off the elements, and pass 3 you can even have 3 and 4 and strike off this elements, I mean strike off this table. If you don't want to create different tables, you can do it in one table itself with ranging from 0 to 4 in each passes or something like that, right? But for this understanding, we are in pass number 3. The first iteration is, we'll compare 4 and 5. Is 4 greater than 5? No. So we don't have any swapping. We'll bring back here. Is 5 greater than 3? Yes. So we do a swapping. So at the end of this third pass, the third element from the right gets positioned correctly. So now in the fourth pass, we left with 5, 7, 9 being perfectly placed. We only left with 4, I mean the array 0 and 1. So we'll check, is 4 is greater than 3? Yes. So we do a swapping, and 3, 4, 5, 7, 9. At the end of this pass, you remember, like n is equals to 5. The total number of passes required to completely sort using bubble sort is n minus 1. So which means 5 minus 1 is 4. So this is our final pass. Something like that. You can even see that this is completely sorted. You don't have to go for another pass like extra fifth pass, because even in fifth pass, all the things, if you can just run them, it's a waste of time. You can check them whether everything is sorted. It is obviously sorted here. From this you can see this 3 gets sorted, and among these 2 this gets sorted. So the comparison is just once. So you remember this comparison here we talked about when we do a theory. When I have pass 1, I have got n minus 1. This is n minus 1 actually. N minus 1 is 5 minus 1 is 4. In pass 2 is n minus 2. So 5 minus 2 is 3. And in pass 3 is n minus 3. So 5 minus 3 is 2. And in pass 4 it is n minus 4, which is 5 minus 4 is 1, right? So that's how it is already stated here. Like this is a pass and this is a comparison, something like that. Now this makes a sense, right? So that's how we have finally reached this pass 4, and finally the given problem, and you can see we have beautifully sorted like 7, 5, 4, 9 and 3. Array 1 is now 3. I'm sorry, array 0 is 3, array 1 is 4, array 2 is 5, and 3 is 7, and 4 is 9. Sometimes some of the terms will stay in the same place. It's based on the order, no? Right? So in this case, all of them have moved. We have a distinct order, distinct movement of the position. Sometimes like 4, for example, 4 is in 2 place, so it can be in to second place itself, depending upon the given numbers and something like that, right? So that's how it is. Like, don't worry, like everything has to be in a different index or something like that. It's not true. And we know the total passes n minus 1, 5 minus 1 is 4 passes, right? So fourth pass will be the final, and total iteration is 10. We have calculated using the arithmetic progression formula, n into n minus 1 divided by 2. So we can even count from this. Leave the 0, like 1, 2, 3, 4. We have 4 plus 3 plus 2 plus 1. So it adds up to 10. Now you can visualize we have got 10 iterations. We have done 10 iterations to completely sort this unsorted list to sorted list using bubble sort. Something like that, right? So I hope you have got some of the interesting idea or the how this algorithm probably works. In the next lecture, we'll be looking into the descending order sorting using bubble sort. See you then. Bye-bye.